Okay, are we sure the microphone works? Good. All right, so today I'll be talking about I'll be giving the second part of the talk from last time. And so the talk from last time was the Concierge formula from quantum field theory. So before I begin, I wanted to just do a short recap of what we saw last time. So last time I wrote down what the Concierge formula was. Gave a little explanation of this. And I also gave you the Moyal formula, which is a special case of the Concierge formula in the case that we are quantizing the canonical symplectic structure on the cotangent bundle of Rn. So I wanted to mention that I forgot some details. So in the definition of the Concierge formula, we had a formula that looked like this. So it was given by a formal power series, and the terms in this power series were sums over graphs of these Concierge weights. So these are numbers that are integrals over configuration space of certain forms, and these are bidifferential operators acting on f and g that depend on a graph gamma and the Poisson structure, that we're trying to deformation quantize. Now, in the definition of the graphs, I forgot to mention that we don't want loops. So any graph that has a loop like this, not allowed. We also don't want double edges. So things like this, not allowed. Okay, that's all I'll say about that. But just in case you were wondering, we don't want these things. Okay, so today I'm going to try to talk about gauge fixing. Specifically,
so this means that you're restricting this Gn, so you're taking Gn such that these two things.
So I gave the wrong definition of Gn last time. The definition of Gn should have these restrictions in it. Yes.
I guess double edges excludes also triple edges.
Yes. So I mean, the reason we could actually sum over double edges, but the reason that double edges are not included is because they give us the same. So these weights are given as integrals over forms, and they will give us sort of the same one form. So the integral will be 0. Whereas these we don't include by convention. So I mean, this double edges comes from the form, and this comes from something called the normal ordering description that I actually mentioned last time in the quantization of the Moyal formula. Okay, so I'll talk about gauge fixing, in particular the BRST method, which is a way of treating gauge fixing by a homological algebra. Then I'll talk about the trivial Poisson sigma model. And deformation quantization of affine Poisson structures. So here at the end, what we will do is we will use all of the stuff that we've been talking about. So we'll use the Poisson sigma model, we'll use gauge fixing, we'll use Feynman diagrams to give the Concierge formula in a very special case where the Poisson structure is affine, so at most linear. Okay. So let's begin with gauge fixing. So far, what we've seen the Feynman diagram method for perturbative calculations of integrals. So let me just remind you, usually we have an underlying space-time M. We have some space of fields. So M is a manifold. Space of fields F, which is somehow, well, it's associated to M. It's somehow you can think of it as maybe a mapping space associated to M or some sheaf on M. The point is that this is, well, if it is a manifold, then it's usually infinite dimensional. We want to integrate over F, this space of fields. So we also, as part of the data of physical theory, have a function from our space of fields to R. This is our action function. And for smooth functions O on our space of fields, we're interested in computing these expectation values. So the expectation value of O is the integral over the space of field of O weighted by the exponentiated action divided by the integral of the exponentiated action. Now, as I discussed a little bit last time, these expressions don't really make sense in terms of actual integrals because we don't have any measure, well, we usually don't have any measure on F, so we have to resort to the Feynman diagram trick, or the use of Feynman diagrams. And remember, the way that this goes is you expand O as a formal power series in the fields F, and you use the Wick theorem. So these Feynman diagram expansions use the Wick theorem, which, remember, we proved in the finite dimensional case, but in the infinite dimensional case, we posited to be true. Yes?
So F, so you take C infinity F, so you take functions from your fields to R. Is this what we do? Or?
Yes. So I mean, we're interested in some, generally speaking, in some smooth function in our space of fields, and we want to integrate it. Yeah, this is, yeah, observable. Okay, and one of the ingredients of the Wick theorem that we needed is that we needed that S have a non-degenerate critical point.
So when you say that you kind of set the Wick theorem to be true, is this meaning that whatever the integration will be, or however we can make sense of that, we will need it to satisfy the Wick theorem hypothesis and stuff? It's rather our definition of the integration.
So, okay. So what I mean by this is that we don't know how to define what these integrals are, but we observe that they are similar in shape, roughly, to Gaussian integrals. And so we have some formulas in the finite dimensional world for the Gaussian moments, so these monomials in X, and then we just posit this to be true. So essentially what we're hoping for is if we could define a theory of integration, then it would give us well, it would give us the Wick theorem. But in the absence of a well-defined theory of integration, we just say, this is true, let's go on.
So the theorem is a definition.
The theorem is a definition, so. But if we had a nice theory of integration, then it would be a theorem. Okay, so this Wick theorem, remember, was, so we had, yeah, this Wick theorem needed S to have a non-degenerate critical point, because essentially what we were doing is we were taking the quadratic part of the action and inverting it. So we needed okay. So this whole discussion is to motivate what gauge fixing is and why we need it. Because in many physically interesting maybe I'll put this in quotation marks because it's a strange phrase. In many physically interesting examples, in many physically interesting examples, our action S has degenerate critical points due to the action of, for example, a Lie group. So for example, if our theory is gravity, then our action is degenerate because we have then our action is degenerate because we have an action of the group of diffeomorphisms. So whenever we have a critical point, we can shift it by a diffeomorphism and get a critical point. So essentially we have a group's worth of critical points, which means that in particular, we can't invert the quadratic part because it's degenerate. So i.e. our space of fields has an action by G, and S is a G invariant function. So the way that we get around this is that if we're trying to compute the expectation value of a G invariant observable, so we take now an observable O that is G invariant. What we want to do is we want to compute this. Somehow this should just be the same as computing over the quotient by G, since everything is G invariant. And this is what gauge fixing allows us to do. Yes?
So you wrote degenerate critical points due to G groups, but other mechanism to degenerate critical points are there?
Well, generally
I mean,
you have some vector fields. These vector fields need not
integrate to a Lie group action.
The algebra action. They're not involved.
In this case, he only considers when you have the group action and you fix the group action, gauge fix the group action, so we don't care about all other critical points to the right, I think.
Okay. Yeah, but you have more general situations where, for instance, the algebra closes only up to the equation of motion.
Yeah, so the distinction here is essentially if this action is given by a Lie group, then I can use the BRST formalism, essentially because this, as Michele was saying, this infinitesimal action, so usually we consider just the infinitesimal action, and in this case, when it is actually an honest action of a Lie group, it integrates, and so it closes. And this is the setting that we can use the BRST formalism in. And more generally, we need to use the BV formalism. And so this is actually the secret reason why, when we do the deformation quantization of affine Poisson structures, we're using BRST. So because the Poisson structures are affine, this infinitesimal action will actually integrate. But if it's got more than linear parts, this Poisson structure, then we need to use the full BV formalism. Essentially because the symmetries look different when we're at critical points than when we're not at critical points. Okay. All right, so what we want to do is we want to define the expectation value of the observable. And so if we are looking at a G invariant function, we've got a G invariant action. We have this action of G on our space of fields. We would like instead to define our observables by integrating over the quotient space. the quotient space of fields by our group action G. Essentially because the only difference between this and this is a factor of the volume of the group. And this factor of the volume of the group appears both in the numerator and denominator, so it's cancelled out. But the problem is this quotient may be bad. And this is what, so to get around this problem is gauge fixing. So the quotient F mod G may be bad, i.e. so it might not be a manifold. We would like to, yeah, it might not be a manifold. It might not be something we really want to consider. So the way of getting around this is via gauge fixing. So the idea is that this integral over a quotient, over the quotient fg, is replaced by an integral over a section, possibly a local section, of this projection map, of the projection to the quotient. So just let me rub off this board and I will try to give a picture of what this should be. Okay, so the idea is to replace an integral over the quotient by an integral over a section. So we have, roughly speaking, this picture here. So this is our space of fields F. And our group action sort of moves everything this way. What we would like to do is just integrate over a slice. Integrate over a slice of this group action. And this is morally the same thing as integrating over the quotient. Okay, so the way that this is done Faddeev-Popov method is you take a section of this projection, which you assume is given, at least locally, by the zero locus of some function I shouldn't use f, should I? Let's say B from our space of fields to the Lie algebra of our group. Okay, so then if we look at the critical locus B equals 0, this is giving us the section that we want to integrate over. So this condition B equals 0 is called the gauge fixing. So in the physics parlance, this group G is the gauge group. The symmetry group is the gauge group. And what we've done is we've fixed it somehow. So this is why B equals 0 is the gauge fixing condition, and B itself is called the gauge fixing function.
Why do you think the algebra value is the good for dimension? Pardon? It has the good for dimension. dimension of the zero set plus the dimension of G is the dimension of F.
Right.
So you want a section of that map, right? Not a section.
No, you want a zero of that.
So of this map, you mean?
You want a section of this map, right?
Yes.
So let's say that actually you want to see this section as the pre-image of this.
Yes.
B
Of
regular
pre-image of 0 by B. Yes.
Right.
And you should have constraints so that this is transversal to the action, right? There's something to add. Or...
Well, this is the same thing as saying that it's giving a section of this, right? So we want a section that locally looks something like a zero locus. All right, so then the idea is that if we take a G invariant function, so I've got G, which is a function on a space of fields that is G invariant. Yes.
So locally, would just mean you take a DG value bundle over F and want a section of this one. Or zero locus.
No, you want to see it as an embedded submanifold. Like take as a pre-image of 0.
Yeah, I guess in F cross. But if you
No. I mean, you have a manifold map from F to the algebra of G, and you see F over G as the pre-image of a regular value, and this is an embedded submanifold.
yes, and you do it locally. So locally you would probably. No, okay.
All right. So we want that so if we've got a G invariant function, we want that the integral of G over F is somehow given in terms of this data. So essentially what we will do is we'll integrate our G invariant function over this section and include a term that compensates for the volume of each orbit. So let's say okay, so our integral of our G invariant function over the entire space of fields becomes this expression. So this delta term localizes the integral to the critical locus of B, so that we are indeed just integrating over this section. And this J of X term, this is called the Faddeev-Popov determinant. Takes into account, so if this is X here, it takes into account the volume of the orbit passing through X. And the reason it's called a determinant is because, in local charts, in a small neighborhood, of the zero section B equals 0, the fiber direction is essentially our group G. But in a small neighborhood, we can use as coordinates, instead of G, it's Lie algebra. So the fiber coordinates of this projection to the quotient can be taken to be, let's see, GI, where GI is a basis for our Lie algebra gamma. So you should keep in mind the finite dimensional case, because otherwise this sentence won't make very much sense. We're doing the standard trick here where we're taking something that is rigorous in the finite dimensional world, trying to understand how it works, and then generalizing it to the infinite dimensional setting. Right. Sorry? Essentially it comes down to the fact that we want to view this term as an honest determinant. And then what we do is, as I've just... Why? Yes. 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 So what we want to do in the end is what we'll end up doing is realizing, so in the case that G is the exponentiated action, what we want to do is we want to make these things exponentials of something as well, so that we can use this machinery of Feynman diagrams. Because we understand if we have something that looks like an exponential that has a non-degenerate non-degenerate quadratic part, then we can use the Wick theorem in order to make these things look like exponentials. So this is already the exponential of something. You just take the Fourier transform. In order to make this thing look like an exponential, we want it to be a determinant.
No, I got it.
Right.
I just don't understand why. Okay. I figure out it.
Okay. All right, so in a small neighborhood of the critical locus, we can take as the fiber coordinates, or the fiber coordinates for the projection, we can take it to be a basis for the Lie algebra. So think in the finite dimensional case here. And then this Jx term is just the determinant Oh, yes. Yeah, so my notes have f and b switched around. So this Jx term is just the determinant of the derivative of b. So you can sort of think of it as somehow a Jacobian factor that is taking into account the volume of this orbit that we're integrating over. Okay, so we want to write this integral. So this integral up here, in the case that we have the exponentiated action, we want to write this as something that looks like this, the integral of an exponential term. Okay, so we can already write this delta B term via the Fourier transform as this integral Okay, so here B of x is valued in gamma in our Lie algebra. So our Lagrange multiplier here will be valued in the joule, and this is just the joule pairing. As for this determinant term, it's slightly more complicated. So we already know from Nima's talk how to recover determinants via integrals of via exponential integrals. So we could do this. What we could do is we could take this matrix and then invert it, and then we would end up with the integral would be something proportional to the square root of the determinant. We don't want to do that. We don't want to do that because in the infinite dimensional setting, this guy will be somehow some differential operator. And we don't want to find its inverse and then exponentiate. This is making our lives a little more complicated. So to realize this as an integral of an exponential term, we'll use the theory of Grassmann integration. So the theory of integration that we all know and love deals with essentially variables that commute. So if we look at if we have a manifold, our integration is an operation that takes place on our algebra of functions, which is a commuting space. So its multiplication is commutative. This Grassmann integration that I'm about to tell you about is a theory of integration for variables that anticommute. It turns out that by considering Grassmann integration, we can realize this determinant as the integral of some exponential term. And let me remind you that the whole point we want to make everything integrals of exponential terms is so that we can use our perturbative methods. So the theory of Grassmann integration is a way of commuting over, so a way of integrating over anticommuting variables. This one. Is that enough? I'll do this. So in the ordinary even/commuting case, we have V a vector space and we take as its algebra of functions usually the completed with respect to degree symmetric algebra of functions on its dual. So this is, in the case that V is equal to Rn, this is exactly just the normal smooth functions on Rn. And so in finite dimensions, we pick a basis. Picking a basis gives us an isomorphism between this and the C infinity functions on Rn, and then this is just the usual theory of Lebesgue integration. Okay, so what I'm going to tell you about now is the extraordinary case, which is the odd/anti-commuting case. So here I have I take as my source material V a vector space. And I look at pi of V. So here, in the even case, we had a vector space, and we were understanding things about V by looking at its functions, by looking at the functions on V. In the anti-commuting case, we do the same thing. So we take a vector space, and then we promote it to an odd vector space. So what does this mean at the level of underlying point sets? Well, we don't actually care because we will examine this object by talking about what its algebra of functions is. So it's the algebra of functions, so the C infinity functions on pi of v, this odd vector space, is defined to be, so you can maybe guess what will happen here. So here we had the symmetric algebra on the dual, and this guaranteed that everything commuted. Here we will have the exterior algebra on the dual. And this gives us anti-commuting things. Notice that we don't have to complete here because eventually, if it's in finite dimensions, high enough powers will vanish. So I should maybe, sorry? Unless it's an infinite dimensional vector space, but let's not go there. Okay, so I'll maybe just mention that it's as in virtually everything phrased in terms of non-commutative terms, it's not really useful to try to think of the underlying point set. We don't have a, we would like to view this as the smooth functions on some point set, but we don't really have enough of an intuition to know what this underlying thing is. So we think about it in terms of its smooth functions. So the reason it's not really useful to think about the underlying set is that I don't think anyone knows what it's supposed to be. I mean, it's probably actually very useful to know what this thing is, but no one knows.
I guess there's just not. It's just an algebra over a point. You should look at sheaves with some additional structure over some base manifold. And in this case, the base manifold is just a point. And everything in this
right.
structure sheet.
I mean, the point is, I guess, that this algebra has nilpotence in it, and this is something that you can't really see at the level of the underlying point set anyway. Yeah. Okay, so for f, a smooth function on our odd vector space, so remember this means that it's an element of the exterior algebra of the dual. We define the integral of f over pi of v as follows. So the first step is to take the projection to the, so this is where the finite dimensionality is critical. We take the projection to the top exterior power. And then after picking a basis, so after picking an ordered basis, this top exterior power becomes isomorphic to R. And this integration operation is just defined by taking something in this exterior power, projecting to the top exterior power, and then composing with this isomorphism to R. Essentially, picking an ordered basis gives us a volume form in that it gives us a canonical element of the top exterior power, and then this integration just compares the top forms, the top parts. I sort of wish that these boards went up just slightly more. Yeah, it has caused me so much trouble over the years. Okay. So maybe one remark to say is that this choice of ordered basis is sort of the odd version of an orientation. Okay, so now if we take B, which is an endomorphism of a vector space, so the endomorphisms of a vector space is the same thing as the tensor product of the dual with itself. So we can view B is a function on function on this odd vector space, which we define. So it's a function on the odd vector space associated to V dual tensor V. And we define this to just be the product. Oh, sorry. Other way around. So it's function on the product of the odd vector spaces associated to V dual and V. And we define this to be the odd vector space associated to this. Okay, so up to sign, picking a basis for V. So picking a basis for V in this setting also gives you a canonical basis for V dual. You just take the dual basis. And this gives you a natural identification of the top exterior power of V dual so there should be a plus here, V dual plus V. Gives you a natural identification of V dual of the top exterior power of V dual plus V with R. And so we can look at the corresponding integration operation. We find that if we exponentiate B, sort of considered as a function on this vector space, on this odd vector space, then we find that the integral of the exponential of B is given by the determinant of B. And this is what we wanted before. We wanted the integral of an exponential to give us an honest determinant, not 1 over a determinant. So there is also a Wick type theorem for Grassmann integration. But I don't think I'll get into that because I'm not sure I strictly need it. Okay. So just to recap, after this digression on Grassmann integration, what we had is we had a function. We looked at our action on our space of fields, which is a function on our space of fields that is invariant under the action of this gauge group G. We had this formula before. For a given choice of gauge fixing function. So now we can write this integral as now as an integral of a new action function, SF, over a slightly different space of. So this SF, well, what we want is that we want its exponential to be given by this term. So this SF includes in it the Fourier transform of this delta function here, and it also includes the corresponding Grassmann term. So remember that this was a determinant. We want to view it as the exponential of some operator integrated over an odd vector space. So maybe I'll write it like this. So we have our classical action. Plus this term coming from the Fourier transform of the delta function, and this term. And we're integrating over x, lambda, c, and c bar. So let me just say what's happening here. So x lives in our normal space of fields. C lives in an odd vector space associated to our Lie algebra, gamma. Lambda, as we saw before, lives in the dual of our Lie algebra. And C bar lives in the odd vector space associated to the dual of our Lie algebra. So, yes. I mean, because essentially these are odd variables. It's the same pairing, but you kind of forget about the thing. Okay, so as I said, this is coming from the delta function, and this term here, so this A of x, is this matrix of derivatives of f by the Lie algebra term. So this integrating this term here, since I'm integrating over odd variables, is giving me exactly this determinant, which is what I wanted.
And this integration is a mix of the usual integration and the one you explained above.
Yes, so this is an integration. So this is a usual integration over x and lambda because these are normal variables, and then a Grassmann integration over c and c bar. Yes, so in the infinite dimensional setting, we now have something of this form, and what we would like to do is we would like to choose A so that its determinant is, well, we would like to choose A in the infinite dimensional setting so that we can make sense of its inverse, and then we can play the same trick getting the Wick theorem, but now for this entire combination instead of just for S of x. So we've solved. The idea of introducing all of this stuff is to solve the problem of x having degenerate critical points by adding extra data such that this whole thing is non-degenerate. Maybe I should mention what the physical names for these things are. This C is called a ghost. This lambda is a Lagrange multiplier. And the C bar is an anti-ghost. Yeah, I kind of like the idea that an anti-ghost is somehow Bill Murray. Sorry? Bill Murray? No. Dan Aykroyd is, I think. Did he? Ah. You can't tell me that while I'm giving a talk. Now I'm sad. Okay. So this is, yes. Yeah, okay, this is going to be tricky. All right, so for a G-invariant function now we can define the expectation value to be this. So I'm going to put so this action here depends on our gauge fixing function B. So I'm going to call this whole action S sub B. So we can define expectation values with respect to a gauge fixing function B as follows. So essentially it's the same expression as before, except now we're integrating with respect to the gauged fix action over this expanded space of fields. And this is by construction giving us the same thing that we had before. So in the finite dimensional case, this is just a complicated way of saying this is what we had before. But in the infinite dimensional case, it gives us the freedom to add to the action more terms to allow a well-defined perturbative expansion. Okay, so here, actually, make some notes. So in the definition of this gauge fixed expectation value, all we needed was the infinitesimal action. So we only needed the infinitesimal action of the Lie algebra on the space of fields, and that's encoded in this term here. This is the infinitesimal action. The full action doesn't appear at all because we're integrating over a local section, and the only term that we care about is really this thing. So we only need the infinitesimal action of our Lie algebra on our space of fields. And we can actually, and I won't get into this, but we can actually relax the requirement that that this function b gives a section. Or a section at all. So we want, so this, if we look at this expression up here, the left-hand side depends explicitly on some gauge fixing function. The right-hand side, I mean, we're trying to compute some expectation value by choosing some gauge fixing. So the left-hand side doesn't, well, the left-hand side does depend on a gauge fixing, the right-hand side doesn't. Yes?
So in this equation of integrals, so the leftmost integral is not defined, right?
Here.
Yeah.
So in the infinite dimensional setting, yes.
And also the middle integral is not defined. For example, this.
I mean, in the infinite dimensional setting, nothing is well defined except this expression here is of the form that allows us to use Wick lemma. And the point is to try to get this guy, where the quadratic part of S is non-degenerate, into a form where we can use Wick's lemma. Because this is how we make sense of infinite dimensional integration. And in the finite dimensional case, I mean, this is just adding some more complication to a story we already know. But yes. Okay. So we want.
So when you say that we can relax the requirement of d minus 1,0 section, still within the BRST framework or like generalizing it?
Within the BRST framework.
Right. And where do you use the fact that this is actually the other?
You mean here? So I mean this determinant. So this term here. So the extra terms that I've added are this term and this term, right? This term doesn't tell us anything about the action.
Right.
This term tells us about the action, but sort of the derivative of the action, the first derivative.
Yes.
So this is the infinitesimal action. This is giving. This is.
The algebra is that, right?
Sorry.
It's just a vector field.
Uh,
You don't need that it's integrable. Yes. Exactly.
no. So we do need that it's a Lie algebra action for the BRST formalism to work, but we don't need that it be integrable.
Oh, you need to have the d square equal 0?
Yes. Yeah, the d square equals 0 comes from the Jacobi identity. And then on the ghost, d squared equals 0 on the fields comes from the fact that it's a Lie algebra action.
If you have a Lie algebra which has a Lie group, you can always integrate.
If it's finite dimensional.
Well, okay,
Right. Let's see. So So in the finite dimensional setting, this all works and is independent of the choice of B. But in the infinite dimensional setting, as Thomas pointed out, none of these three things actually make sense. I mean, this kind of makes the most sense because we can wrap our heads around it and understand it. But this depends very explicitly on the choice of B, on the choice of our gauge fixing function. So in the infinite dimensional setting, we want, so in infinite dimensions, we want conditions under which this gauged fixed expectation value is independent of our gauge fixing function B. So if we can guarantee that this is independent of our gauge fixing function B, then it's called gauge fixing independent. Okay.
Can I say one thing? Just so even if this thing doesn't make sense, this whole series of inequality, this story of the RST and general resolution and extension of the space of fields and stuff has a meaning in classical
Yes.
physics. So there it makes sense, and then you can try to see if this helps for quantization. So it's not like a complete waste of time to do.
So I mean,
Even if the series of expressions there do not make sense.
yeah. So what we're about to do is look at the Brst formalism, which is a way of understanding when these things ought to be gauge fixing independent in the infinite dimensional case. But what the Brst complex actually does, so the Brst formalism takes our space of fields and it uses the fact that we have an infinitesimal action of a Lie algebra on our space of fields and constructs from this some complex. So it constructs from this some guy with a differential. And this is really encoding the information of the quotient space. So you can make this more precise by viewing the quotient space as a stack, but this is sort of somehow the machinery that's going on in the background. Okay, so we can say under which conditions this will be gauge fixing independent. So I'm going to write down a theorem. So this theorem is true in finite dimensions when everything is finite dimensional and is assumed true in infinite dimensions. So finite dimensions tick, infinite dimensions assumption. And it is that if we have an infinitesimal action x of our Lie algebra on our space of fields, then if S and G are invariant functions, so invariant under this infinitesimal action, and the divergence of the vector field associated to gamma plus the trace of gamma in the adjoint representation equals 0 for all elements of gamma, then the expectation value of this function with respect to the gauge fix with respect to B is gauge fixing independent. Okay, so the reason that this works in finite dimensions but doesn't work in infinite dimensions is we use here this condition on divergence. In order to define divergence, we need to know what a measure is. In particular, we need to know how to integrate. So this is sort of all wrapped up in the infinite dimensional story. I mean, we would like to say that it's gauge fixing independence, but we need to know what the integration is in order to say that it's gauge fixing independent. So we just, in the infinite dimensional case, we sort of assume this to be true and then proceed as if it's true, and then any divergences from what we expect are called anomalies. Okay. So we'll actually see more or less the proof of this theorem using the Brst formalism. So the Brst method is named after Becky, Ruhe, Storer, and Teuton. It's roughly speaking a way of doing gauge fixing via homological algebra. So in the setting that we have up here, we have an action of a Lie algebra on our space of fields, an infinitesimal action. This tells us that our smooth functions on the space of fields is a module for our Lie algebra. So we can consider the associated Chevalier-Eilenberg complex. So that is the complex given by taking exterior powers of the dual of the Lie algebra tensored with C infinity functions on our space of fields, and it has a differential delta. So delta is a derivation on the exterior algebra component that acts by vector fields on the smooth functions on the space of fields. So explicitly, if I pick a basis, so again, I'm in the finite dimensional setting, otherwise I can't pick a basis. Well, I can, but let's not get into that. So if I pick a basis EI of gamma, our Lie algebra, we get a dual basis Ci of our of the dual vector space of our Lie algebra. So I'm choosing Ci here to be consistent with our notation that we had before for ghosts. So you should think of these as our ghosts. Then in order to work out, so in order to define what the differential does, we have to say what it does on a smooth function and also what it does on these basis, on this basis for gamma star. Because once we've done that, then since it's a derivation on lambda gamma star, then we have the whole action. So what it does on Ci is this. So here, these Fij, these are the structure constants of the Lie algebra in this basis. So that means if I take the bracket of Ej and Ek, I will get some linear combination of the basis again, and the structure constants are given by this formula. So this you should view as encoding the bracket. This is encoding the bracket of the Lie algebra. I mean, you can sort of see that because this expression uses the structure constants. And so for f, a smooth function on our space of fields, delta of f is given by this expression. So this is exactly the infinitesimal action. Okay, and just as an aside, the fact that, so we want this to be a complex, so we want d squared, we want delta squared to be equal to 0. The fact that delta squared equals 0 on this generator is the same as the Jacobi identity. And the fact that delta squared is 0 on f is encoding the fact that this action is a Lie algebra action. Maybe I'll leave the theorem up there. Okay, so notice that so far what we have is we have a derivation acting on this space. So this space we view as space of C infinity functions on pi of delta star cross F. Remember before we had F tilde, which was F cross, oh, let's see if I can get it in the right order. Oh, sorry. F cross pi gamma star cross pi gamma star. Okay, so we have at the moment we have a derivation acting on the functions on this first part. A derivation acting on functions is a vector field. So we have at the moment a vector field on a space of fields F, a space of classical fields F, across the odd vector space associated with gamma. We can extend this to the whole space of fields. F tilde. So what we need to do to extend to the whole space of fields F tilde is to give a derivation on this complex. So just for clarity, our ordinary functions live here, our ghosts live here, our Lagrange multipliers live here, and our anti-ghosts live here. Okay, so I define a derivation on this whole guy by saying, well, what we had before acting on the C and the F, and I say that delta of Cj equals lambda j, and delta of lambda j equals 0. And so this is now clearly a complex. Okay. So we view this delta as a vector field on F tilde. Well, why is it a vector field on F tilde? Because it's a derivation for its algebra of functions. And that means that, well, at least in the finite dimensional case, we can define its divergence.
So rho is the actual.
Where is rho? S. This is symmetric algebra. Okay. So we can actually show that the divergence of delta will be given by divergence of x gamma plus the trace of ad gamma. So this expression here. We're going to use that in the proof of this. Oh, yes, small gamma. What? Yes. So I mean, what in the finite dimensional case, we assume that we have a measure on F, and this is essentially just Rn. So it comes with a canonical measure, and this is, as I said before, and here picking a basis gives a canonical orientation up to sign. So essentially, there's not really any ambiguity. Well, not very much. Okay, so. Right. Where was I? Okay, so our gauged fixed action. A gauge fixed action from before, SB. So let's write it out again. So it's S plus the pairing of lambda with B of X minus the pairing of C bar A X C. And here this A is arising from the infinitesimal action. We can actually write this as S, so that part doesn't change, plus delta of psi B. And this psi B is equal to this. Well, whoops. So remember that this B is valued in the Lie algebra, so this is just summing over components. This is called our gauge fixing fermion. So the reason that it's a fermion is because these C bar variables are odd. Anything that is, well, Anything that is odd is a fermion, anything that is even is a boson.
So you want to say that this whole thing that we're doing is because we want an additional symmetry for this SP, right? So you want that when you act with this delta, then you get something that is.
Well, I mean, I mean, in the proof of this theorem, we'll see why it's important to have it in this form. I mean, essentially because so in this theorem, if S and G are invariant functions, then this means that delta of S and delta of G equals 0. And so we'll end up integrating something that is delta closed. Well, integrating something, yeah, that is delta closed. Okay. So lemma, if delta of G, so if G is now a function on this extended space of fields F tilde, if delta of G is 0 and divergence of delta is 0, then this integral I sub B, which is the integral over the space of fields of the exponentiated gauge fix action against B, this is gauge fixing independent. Okay, so the proof goes as follows. What we do is we take a path of gauge fixing functions. So T goes to BT. This gives a path of gauge fixing fermions just by plugging into this expression. And then we can take the differential of this integral with respect to T. So the derivative with respect to T of I BT. This is going to be, well, so in this expression, the only thing, when B depends on T, the only thing that depends on T is the gauge fix action. So we end up with this formula. Okay, so in the next step, we use the fact that delta of G is 0 and delta of E I H bar SB equals 0. And this comes from the fact that our classical action S is invariant under the infinitesimal action of our Lie algebra, and because delta squared equals 0. So this we can write as IH bar integral over F tilde of this whole junk here, which by the definition of the divergence operator, so if we integrate delta of some guy, by the definition of the divergence operator, this is the same as integrating the divergence of delta multiplied by this function. And this is now 0. Okay, so what we've shown here is that if we have a function on our extended space of fields that is closed under this delta, and if the divergence of delta equals 0, if we're integrating with respect to an invariant gauge fix action, then the result does not depend on the gauge fixing. So in particular, this lemma implies this theorem above, because the divergence of delta is given by this term.
What was saying Albert in this case, but in case the divergence of delta is not 0, it's anomalous? That's what you were saying?
Yeah, more or less. I mean, so the problem is that in the infinite dimensional case, we can't make sense of this. So we just sort of assume that it is true and then proceed. And then there are some, if this is true, then there are some relations that should be true between certain expectation values. And we can compute these expectation values and then compare them. And if these relations are not true, then this is indicating that at some level, this is not true. And that's an example of an anomaly. Sorry, can you repeat that?
Usually, we don't compute. This is sort of expectation value. This integral I, it's not.
Yes, so this integral I mean, the expectation value is built up of a quotient of such integrals. Yeah. Yeah. And this delta G is 0. So maybe I should have said, if O, so this is the observable whose expectation value we want to compute. So remember that F tilde is built up of our space of fields across some other stuff. We can view this as a function on F tilde. And then saying that delta of O equals 0, well, since this O doesn't depend on any of the extra variables we've introduced, delta of O equals 0 is exactly the same thing as saying that O is invariant under the infinitesimal action. Yeah, so in particular, if G, this function G on F tilde is really coming from a function on our ordinary space of fields, then this is saying if it's invariant under the action, then this gauged fixed expectation value does not depend on the choice of gauge. Yes?
So if I remember correctly, then in semi-classical quantum mechanics, the fermion was something which had some, what was it? Some odd behavior, some odd symmetric behavior under spin substitution or something like this.
Mm-hmm.
And the boson was, it had just symmetry on the nose, right? So, which lead also to some consequences like fermions can only populate certain energy levels to some extent.
Right.
Bosons are, you have Bose-Einstein condensates and so on. Do you have similar phenomena like these statistics or the symmetry behavior?
If you view
type of gauge fixing fermions? Or where does this
yeah.
symmetry come from? Where is it motivated from?
The analogy is just because it's odd.
Yeah.
You call it a fermion. But I mean, it's not a physical object, and these are just auxiliary variables.
Yeah, so you don't view this as an actual particle per se. I mean, these C and C bar variables, these are odd variables. These are somehow fermions that are entering into your system, but these are imaginary particles. Because
you also have Feynman diagrams for these ghosts.
Yeah.
The ghosts, but I mean, in the end, you don't compute anything that you can observe because these are not physical particles.
so in these Feynman diagrams of, for example, Yang-Mills, when you introduce these ghosts, then you have the diagrams that include interactions of these virtual particles. But you don't view them as actual particles. You don't want to calculate scattering amplitudes that involve these particles inputting these particles and coming out.
You want to exclude them from the input and the output,
Yes.
but internally you have them and they give corrections
Yes.
to the amplitude you compute. So, and you
No,
can measure.
they're
but
just there to enforce the symmetry, the word identities and stuff like that. So they are there for the sanity of the theory.
So if you compute say the scattering amplitudes, there is no,
you don't see that. They're not physical. You cannot actually compute stuff with them.
I cannot tell you like on top of my head why, but we'll discuss it.
I mean, yeah, the way that I see them as coming about, and this is not really a physicist's point of view, but the way that I see them as coming about is you add them as corrections so that your perturbation expansion makes sense. I mean, this is not a very physical way of looking at it, but that's how I understand where they come from.
Yeah, okay, but this doesn't explain the terminology fermion. So.
No, I mean, I think the terminology fermion just comes from the fact that it's odd.
Yeah, but nature means okay, let's go on.
Yeah. Okay, so we've shown that if delta of G equals 0, then its expectation value is gauge fixing independent. And in fact, sort of basically this exact same argument shows you that if G is delta of F, then its expectation value is 0. So this means that, so maybe I should put a gauge fixing function down here. This means that taking expectation values is an operation on the cohomology of this operator delta. So it's an operation on delta cohomology, and it is a locally constant function on the space of allowed gauge fixings. Provided you can connect two gauge fixing functions by a path, then they will give you the same expectation value. Okay, and so it is in this sense that I mean that the problem of gauge fixing becomes an operation in homological algebra. So in this setup, what we want is we want to tweak the action by a term so that we can actually do a perturbative expansion in the sense of Feynman diagrams. And then we know that the result should be morally, well, yeah, this argument, if it were to carry over to the infinite dimensional case, then if we had an invariant function, we would know that the result should be independent of the gauge fixing that we chose. So the infinite dimensional world is a little bit more pathological than we'd like, but this is the intuition that we're bringing to the game. Okay, so let me just say some quick words about the infinite dimensional case. So in this case, our space of fields F is infinite dimensional. We have an infinitesimal action of a possibly infinite dimensional Lie algebra, and we have an invariant action function. Okay. I mean, it can be the Lie algebra of the, I mean, for example, it can be the Lie algebra of the group of symmetries of a G bundle.
Okay, so you're taking infinite dimensional cases.
Everything can be infinite dimensional. Okay, and then we have that this assignment of a class in delta cohomology to its expectation value. And this assignment goes via these perturbation expansions. So in the finite dimensional case, this is an honest to God integral. In the infinite dimensional case, we have to make sense of it. This should be gauge fixing independent. Whenever the divergence of this delta operator equals 0. So I've mentioned this already a couple of times. This doesn't really make sense because this assumes that we know how to integrate to begin with. And that's the problem we're trying to address. So one way that we can get around this is by, we can define divergences via expectation values. So the divergence of a vector field X should obey this formula. So if I have a vector field X, the divergence of X, if it exists, is an observable such that this is true. And this is essentially what you get if you take the normal definition of divergence and you interpret it via expectation values. So in practice, even this, it's very difficult to make sense of what the divergence is. So in practice, we just take this to be true. We use this to derive properties of Feynman diagrams, and once everything is more or less properly defined, we check identities. We check identities that this would give us. So for example, the relationship between different gauged fixed expectation values and any deviations from what we expect. Had this have been true, these are called anomalies. Okay, so maybe let me rephrase the upshot of all of this. So the upshot is we have a system, we have a physical system with a symmetry spoiling the non-degeneracy of the action. So in the BRST method, we can address this non-degeneracy problem by adding terms to the action to calculate expectation values of invariant functions. And this should be an operation in the cohomology of delta. So this should somehow be encoded in something homological. Okay. Something tells me that I won't get through this in the next 10 minutes. Right. Well, I'll think about what I should do and clean off some boards. Okay, so maybe I will. I don't know that being very sketchy is going to cut it. Okay. So why is this discussion of gauge fixing needed? Well, because we want to obtain the Concierge result. So we want to obtain the Concierge formula for deformation quantization in the case of Rn equipped with an affine Poisson structure. And here we have some symmetries. So we have some symmetries that are spoiling the non-degeneracy. We have some symmetries that are spoiling non-degeneracy, so we need to do some gauge fixing in order to calculate expectation values. So the Concierge product is given by calculating a specific expectation value of a quantum field theory called the Poisson sigma model. And the reason here that we need an affine Poisson structure is because these are the ones that BRST work for, this BRST formalism. So more generally, we would need the BV formalism. So the BV formalism you can sort of think of as an extension of the BRST formalism that does a more general version of gauge fixing. So we need the BV formalism. And the reason for this is because we want to interpret the calculation of these gauge fixed expectation values as an operation in the cohomology of this delta. In the case that this Poisson structure is not affine, delta does not give you a good cohomology. In fact, it doesn't have a cohomology. So delta squared, so in this case, delta squared equals 0 when we have the classical equations of motion. Delta squared equals 0 when we have the classical equations of motion of this Poisson sigma model, but away from the classical equations of motion, it's non-zero, so we don't have a well-defined cohomology. So we don't have a well-defined BRST cohomology in the case that this Poisson structure is not affine, and so we say that the BRST method is not available. Right. Okay.
You mean that it's equal to 0 only for specific elements of F, not for all F?
Yes. Yes. Exactly. Okay, so maybe I can at least try to talk about the trivial Poisson sigma model. So the idea of the way that we get the Concierge formula for an affine Poisson sigma model is we take the trivial Poisson sigma model and use this to calculate, well, we use this to get Wick's theorem after doing some gauge fixing by BRST. And then we view the affine Poisson sigma model as a perturbation of the trivial guy. What this means is that, so in the case of the trivial Poisson sigma model, we will end up computing propagators. So these propagators are these two-point functions that appear in the Wick's lemma. We will compute the propagators for the trivial Poisson sigma model and then use these in the expectation values, in the computations of expectation values for the affine Poisson sigma model. Right. So maybe I can at least say what these things are. So the trivial Poisson sigma model Well, what is a Poisson sigma model? We need a Poisson and we need a sigma. Here's our sigma. Here's our Poisson. That's what it is. Okay, so essentially what we're doing is we're mapping, M is the model, yes. So we're mapping some surface into a Poisson manifold. And in the cases that are relevant to the Concierge quantization, M is always Rn. The surface has no extra structure. No, we need to integrate over the surface. Yeah.
But here it's the compact oriented.
So in the example, so the Concierge quantization comes from when the surface is the upper half plane, but you equip it. So as part of the gauge fixing, you need to pick a metric, and this metric is the hyperbolic metric, so it's sort of equivalent to the disk. Yeah, I mean, these are nice things that you can integrate over. They're all orientable. Okay, so the trivial. Okay, so let me just define for you the trivial Poisson sigma model on the plane. So in this case, I'm looking at maps from R2 into Rn equipped with the trivial Poisson structure. So the Poisson structure is 0. My space of fields is 0 forms on R2 valued in Rn that vanish at infinity, together with 1 forms on R2 valued in Rn that vanish at infinity. So I'm going to call these eta upper I, so psi upper I, eta lower I. And then our action is this. So we take one of these smooth functions and sort of decompose it into its different pieces in Rn, and then we differentiate, and that's this d eta I. This is, well, it's a 1 form on R2 valued in Rn, or n 1 forms on R2, and then we take the wedge product of the corresponding components, sum all of these up, and then integrate. Okay, so the symmetries of this system, since eta is constrained to vanish at 0, the symmetries of this system are just eta plus d of some guy, where this guy is again an Rn valued form on the plane that vanishes at infinity. So this is our Lie algebra of symmetries. And then perhaps in a later edition of this, I will explain how to use BRST to gauge fix away these symmetries and actually compute propagators for this. So yeah, sorry, I didn't get anywhere near where I wanted to get, but hopefully it wasn't a horrific experience for you all.
Thank you.
All right.
So I was afraid that I was arriving